following is made possible through a grant from the University of California, San Diego's Instructional Improvement Program. All rights reserved. Significant figure measurement and calculations in chemistry, presented by Dr. Carl Hager, PhD, the University of California, San Diego, Department of Chemistry and Biochemistry. For information on how to contact Dr. Hager, please see the last slide in this presentation. This is part 2, Calculations in Science, Dimensional Analysis. This is the second part of our discussion that started with significant figures. What we're going to do is talk about where we use significant figures, and that is in dimensional or in calculations in chemistry. And we're going to talk about how we do those using what's called dimensional analysis. What is dimensional analysis? It's also what's known as the factor label method. And it's a way of problem solving. It's a way of problem solving that simply says that if we follow our units, and our units at the end are correct, given that we've done the math correctly, our answer will be correct. A quantity, dimensional analysis, a quantity in one unit or one type of unit is converted into an equivalent quantity in a different unit. For example, conversion of grams to pounds or inches to miles. It is a way to analyze and solve problems by using the units or the dimensions of the measurement. It's based on the correct assumption that the units of your answer are correct. It's a good chance that your answer will be as well. You use the units to solve the problem, and you'll actually do the math at the end. It requires the use of what are called conversion factors. These are equivalent statements that allow us to convert units of one type into another, and that's what we're going to spend most of our time here talking about. Conversion factors, slide 5, are derived from equivalent statements. An equivalent statement is nothing more than an equality, something that relates one quantity to another. You can write it in equation form if it's not already. For example, 1 foot is 12 inches. There are 15,125 volts in a Saturn view. A mole of carbon atoms weighs 12.01 grams. And as you can see on this slide, I've turned those from words into actual equations. 1 foot equals 12 inches. 15,125 screws equals 1 Saturn view. 1 mole of carbon equals 12.01 grams. Remember that these are statements that link one quantity to another. It's not saying, for example, that 15,125 screws is what a Saturn view is made of. It simply says that's what it contains. It's a little bit tricky in that regard, but a conversion factor allows us to take pieces of one thing and convert them into another. Conversion factors are most useful, in fact this is how we're going to use them, when they're expressed as what's called an equivalent ratio. In other words, 1 foot equals 12 inches can also be turned into a ratio. 1 foot for every 12 inches, 1 foot divided by 12 inches, or 12 inches for every 1 foot, or 12 inches divided by 1 foot. 1 mole of carbon, for example, divided by 12.01 grams, or 12.01 grams divided by 1 mole of carbon. These are ratios that we're going to use when we solve these kinds of problems. It's important to remember one thing when you look at these equivalent conversion factors, these equivalent statements, these equivalence ratios, and that is when the 1 appears by itself in an equivalent statement or a ratio, that 1 is an exact number. And if you remember from significant figures, our discussion before, that means that there is no number of significant figures associated with that number 1. It is 1.0000000 on into infinity. It is an exact number. Well, on the next slide, let's look at the equivalence ratios. Let's examine how an equivalent statement is converted into an equivalence ratio. And the reason we do this is because it's useful to see what we're really doing. So let's say, for example, we talk about pressure. In pressure, there are two units. There are two unit systems we use. One is what's called the atmosphere, abbreviated as ATM. The other one is what's known as a Pascal. If you have 1,000 pascals, you have what's called a kilopascal, or a little k, capital P little a, or kPa. So one equivalent statement is that 1 atmosphere is equal to 101.325 kilopascals. Well, if we take this equation and we divide both sides by 101.325 kilopascals, we wind up on the left with 1 atmosphere divided by 101.325 kilopascals. That's our equivalence ratio. But it's interesting to see what happens on the right-hand side of the equation. Notice the right-hand side of the equation has 101.325 kilopascals divided by 101.325 kilopascals, which is 1. We can do the same thing if we divide both sides by 1 atmosphere. We get a different ratio. We get 101.325 kilopascals for every 1 atmosphere is equal to 1. So what is an equivalence ratio? What is a conversion factor? It's a creative way to express 1. On slide 7, we can see some more things about conversion factors. For unit conversions in the same measurement system, i.e. from metric to metric or English to English, conversion factors are defined quantities and therefore have unlimited numbers of significant figures. So for example, converting 2 millimeters to 2 nanometers, to centimeters, 2 nanometers is equal to 2 times 10 to the minus 7 centimeters. That conversion is an exact conversion, and there are unlimited number of significant figures with it. Converting 16 ounces to pounds, 16 ounces is equal to 1 pound, so converting ounces to pounds is an exact conversion and has an unlimited significant number of significant figures. When we do unit conversions between different systems, for example, from metric to English or vice versa, conversion factors are measured values and do have significant figure limits. So conversion within the same system, we don't have worry about the number of significant figures in the conversion factor, but we do when we're going between them. So for example, if I were to ask to do the conversion between feet and meters, that conversion does indeed have significant figure limits on it. There is one exception, however, and that is that 1 inch is equal to 2.54 centimeters. This is an exact conversion and is the only one. It is an exact conversion between inches and centimeters. And you may ask, why is the case? And this is because it was deemed by an act of Congress that this conversion factor should be exact. It is the only one. Quite often, when we don't want to have to worry about significant figures in converting measurements or distance measurements, you'll often see the conversion go from English units down to inches and then to centimeters and then back up to the metric units that we're interested in. Equivalent statements also have another relationship. If you have a big number of a small unit, you'll have a small number of a big unit. So for example, 1,000 millimeters is 1 meter. A millimeter is a small unit, so a lot of that is going to be equal to a small number of a bigger unit, for example, in this case, the meter. 6.022 times 10 to the 23rd atoms is 1 mole. Once again, a small unit, an atom, and a big unit, a mole, and you can see we have big number of a small unit, small number of a big unit. If we continue on to the next slide, we see that the units in a conversion factor can be treated the same way that you treat numbers. They can be squared, rooted, canceled with identical units, etc. In fact, this is one of the most important and one of the most useful parts of doing dimensional analysis or factor label method. For example, let's say I wanted to be able to convert between cubic inches and cubic centimeters. Well, I could look all over Earth and I might not find, of course nowadays there's Google, but I might not find in any book that I looked at how to do that conversion. But I do know what the conversion is between inches and centimeters. 1 inch is equal to 2.54 centimeters. Let's take that ratio, 2.54 centimeters for every 1 inch, and let's cube it. Because if we cube that quantity, centimeters becomes centimeters cubed and inches becomes inches cubed. Well, just because we cubed the unit doesn't mean that we don't do it to the number part. In fact, we do. We have to cube the numerical. So the numerical portion gets cubed, so we get 2.54 cubed centimeters cubed for every 1 cubed inch cubed, gives us a conversion factor between cubic centimeters and cubic inches of 16.4 cubic centimeters for every 1 cubic inch. So now, if we were to ask how many cubic centimeters does 15 cubic inches represent, we take 15 cubic inches, we multiply it by our equivalent statement, 16.4 cubic centimeters for every 1 inch, for 1 cubic inch. Notice that the inches that came with the 15 are canceled by the denominator, inches cubed, in our conversion factor. And so we're left, after canceling those units, with cubic centimeters. And so 15 cubic inches is equal to 246 cubic centimeters. Now, since I'm using significant figures, excuse me, once again, since the number of significant figures we have in our starting point is 15, we can only have 2 significant figures in our answer. And while that's not shown on this slide, it would be 250 cubic centimeters, or if we did the rounding, of course, or 2.5 times 10 to the 2 cubic centimeters. Conversion factors therefore allow us to convert one measurement in a given set of units into another one. Well, continuing along on the next slide, slide number 9, conversion factors can also be derived from physical properties. They can be derived from chemical measurements or constants. For example, the density of mercury is 13.55 grams per cubic centimeter. By the way, there is a conversion that you should know at this point in time. I don't believe it's on any of these slides, and that is that a cubic centimeter and a milliliter are the same thing. 1 cubic centimeter is equal to 1 milliliter. That's a thing you want to remember because it shows up a number of times. As a result, density can be expressed as either grams per cubic centimeter or grams per milliliter. At any rate, here's the density of mercury, 13.55 grams per cubic centimeter. Another constant another number we can get is the heat of vaporization of mercury. This is 15.23 kilojoules per mole. Also, there's a constant. This is known as Planck's constant. Planck's constant is 6.626 times 10 to the minus 34 joule seconds. It's not a per second. This is actually one where it's joule seconds. Conversion factors derived from physical properties or chemical measurements are considered measured quantities and therefore have significant figure limits. It's therefore important to use the most precise value you can find when using them and apply significant figure rules as needed. For example, mercury, if I look it up in a more accurate reference book, will have a density of 13.55 grams per cubic centimeter. That's 4 significant figures. But many books which simply report it as 13.6 grams per cubic centimeters. In this case, it has 3 significant figures. As I said in the previous discussion about significant figures, more often than not, your conversion factors are never going to limit the number of sig figs that you can have in an equation or in a problem, because they usually the number that you're given is going to have enough significant figures for whatever work you need to do. Constants also have significant figure limits. Most constants have values with such high precision that it's rarely necessary to invoke significant figure rules. So for example, 8, Planck's constant, is, if you want to use the really accurate number, it's 6.626075 times 10 to the minus 34 joule seconds. It's commonly, all those digits are not used. Commonly, we just simply use 6.626 times 10 to the minus 34 joule seconds because it's rare that the quantities that you're given in the problem have more significant figures than 4, so this is plenty for what we need. Well, conversion factors are great. How do we do dimensional analysis? That would be a good thing to pick up this time. Dimensional analysis is very easy to do, as long as you're careful. You simply begin by creating a conversion path. Simply put, what do you have, what do you need, and what do you know? You want to take what you have or what you start with, what you need to get to, and then string together conversion factors that are going to let you do this. You need to determine what equivalence ratios or conversion factors are going to be needed. You then put the conversion string together, adjust and cancel units as called for, put in actual numerical values, do the math at that point in time, and do it carefully. And then finally, the last thing that you always have to do in these is ask yourself, does the answer make sense? Now, in the slides I'm going to show you from here out, I'm actually going to put conversion strings together. And this is easiest for me because this is how I learned it. For many people, in fact, many students, find that in the beginning of doing dimensional analysis, it's much easier if you simply do one conversion at a time. Take the answer there into another step, apply another conversion factor, take that answer and apply another conversion factor there. Whichever way you find most useful for you, that's the way that you should do it. You want to do it the way that gives you a correct answer every time, rather than try to do it the shortcut way that it's going to look like how I'm doing it. So let's take a look at the next slide and look at our first example. A ruler is 12 inches long. How long is it in meters? If I give you the fact that 1 inch is 2.54 centimeters, the first thing we need to do is set up a conversion path. So we have inches, we're going to meters. We know that from inches we can get to centimeters. 1 inch is equal to 2.54 centimeters. Can we get from centimeters to meters? Well, yeah, they're both in metric. So centimeters to meters, 100 centimeters is equal to 1 meter. So here I have my conversion path. Go inches to centimeters and then centimeters to meters. Put the string together. 12 inches times 2.54 centimeters for every 1 inch times 1 meter for every 100 centimeters. Notice how the cancellations go. Inches cancels the inches in the denominator of the first conversion. Centimeters cancels centimeters in the denominator of the second conversion. The only units left are meters. So then do the math. 12 times 2.54 times 1 divided by 1 divided by 100. That's just simply what the math is. Gives me 0.3048 meters. I'm only allowed two significant figures because I started with that 12. So my answer is 0.30 meters. That's two significant figures. All the conversions we use, notice, are exact. Well, let's look at another dimensional analysis example, and this one is a much more complicated one. So let's take a look at this first, what we got here. Jules Verne wrote a book, 20,000 Leagues Under the Sea. How far is this in feet? It's much more difficult, mostly because you got to use a lot of uncommon conversions. 1 league is 3 nautical miles. 1 nautical mile is 10 cable lengths. 1 cable length is 100 fathoms. 6 feet is 1 fathom. So let's set up a conversion path. We're going to go from leagues to feet. That's why I have the question mark there. Well, let's see what we can do. Well, I can convert leagues to nautical miles. 1 league to 3 nautical miles. That's a 1:3 ratio. Nautical miles to cable lengths. 1 nautical mile to 10 cable lengths. Cable lengths to fathoms. For every 1 cable length, there's 100 fathoms. And then finally, from fathoms to feet, there's 1 fathom for every 6 feet. So let's put the whole string together. This is shown on the next slide. Now, once again, what would, for some people, might find it easiest to simply take 20,000 leagues, convert that to nautical miles. Then take that answer, convert the nautical miles to cable lengths. Take that answer, convert the cable lengths to fathoms. And then finally take the fathoms and convert it to feet. I put them all together in one string. 20,000 leagues times 3 nautical miles for every 1 league times 10 cable lengths for every 1 nautical mile times 100 fathoms for every 1 cable length times 6 feet for every 1 fathom equals 3.6 times 10 to the 8th feet. Since we only have one significant figure we're allowed to use, that's the 20,000, the answer is 4 times 10 to the 8th feet. It's one significant figure. Once again, notice leagues cancels leagues, nautical miles cancels nautical miles, cable lengths cancels cable length, fathoms cancels fathoms. The only units that we have left over are feet. It's important to set these things up like this. Remember, something in a numerator can only cancel something in a denominator. Something in a denominator can cancel only something in a numerator. Two numerators when multiplied together, or two denominators when multiplied together, do not cancel. So you've got to be very careful into these circumstances. Well, let's look at this third dimensional analysis example. And this one is a more common one that we see in chemistry. So let's say that we have a 0.032 molar solution of HCl. Molarity is a unit that's used in chemistry to talk about something called concentration. A molar solution is a solution that has 1 mole of something per liter of solution. So if we have something that is 0.032 molar, that means we have 0.032 moles of that material for every 1 liter of solution. So let's say that we have a 0.032 molar solution of HCl, that's hydrochloric acid, and let's say that it has a density of 1.17. How many milliliters do you need to measure out to ensure that the volume you have contains 7 grams of HCl? On the surface, this looks like an extremely complicated problem. It actually isn't. One of the reasons that it's not is, or I should say, one of the reasons it looks complicated has to do, first of all, that you're given a value that has no units. You're given the density. Density is 1.17. Well, you have to know the density is always in grams per milliliter, or grams per cubic centimeter. Remember, cubic centimeters and milliliters are interconvertible. So you have to know that, and that's one of those kinds of things that's just going to show up. You just have to kind of know it. You also have to know that molar is moles per liter. These are very common problems that show up a lot of times when we're doing this. Let's say, now, there's one other problem I want to point out here, and this is not something that you would see right off the bat. You're given too much information in this problem. We're telling you that a 0.032 molar solution of HCl has a density of 1.17. Well, if density is in grams per milliliter and 0.32 is in moles per liter, well, it seems like we have too much information, and we do. The 0.032 molar is a superfluous number. It's not needed. It's simply something that we're telling you about the solution. To solve the problem, we don't need it. We need to know the volume of HCl that contains 7 grams of HCl. Well, what do we know? We know the density of solution is 1.17 grams per milliliter. Therefore, we have something that converts grams to milliliters, or milliliters to grams, depending on the way you use it. The molarity is not needed. So we set up a conversion path, starting this time with what we need. We need grams of HCl. We have grams of HCl. We need to know how many milliliters of HCl. We know that 1.17 grams per milliliter is density. So put the string together. 7.0 grams of HCl needed times 1 milliliter of HCl for every 1.17 grams of HCl. Notice grams of HCl cancels grams of HCl. And by the way, milliliters of HCl does not cancel. That is a mistake on this slide and will be fixed in later versions. This is equal to 5.98 milliliters, which is equal to 6.0 milliliters. Remember, the milliliters of HCl did not cancel. That was just a mistake that I didn't have time to fix before I got these things out. Now, what about multi-step problems? These are also very common. Multi-step problems are more complicated dimensional analysis. Usually they involve complex units. Values naturally expressed as a ratio where the units may be understood. For example, gas mileage. We know that gas mileage is miles per gallon. Speed can be in miles per hour or inches per second. There we sort of have to know the field that we're working in. Density, molar mass, these are other examples of understood units that make a quantity up. To do multi-step problems, the strategy is to solve the problem by breaking the solution into steps, and then to convert the complex units using dimensional analysis. Many tasks you do in daily life are complex, and we handle them by simply breaking them down to manageable parts. We're going to do the same thing for dimensional analysis of multi-step problems. For example, when you clean a car, how do you do it? Well, You vacuum the inside, then you wash the exterior, then you dry the exterior, and you apply a coat of wax. You may do other steps in this, but just broken down to these steps, it's not a very difficult task. Well, let's take a look at a multi-step problem example. I'm going to go through this relatively quickly because you can always come back to it. You're driving your sports car to Tahoe at an average speed of 68 miles per hour. After 250, and that period means 250 exactly minutes, you decide to stop for lunch. How many kilometers have you driven in this time, and how much money have you spent on gas to drive this distance? Your car gets 32 miles per gallon. Gas costs 82 cents per liter. There may be more than one way to approach problems like this. I'm simply going to show you my solution path for this. I'm going to start by determining the time in hours I spent driving. I'm then going to determine the miles driven. I'm going to determine the kilometers driven, and then finally determine the money spent. There are some unusual conversions needed. I've put those on here. 1 mile is equal to 5,280 feet. 1 inch is equal to 2.54 centimeters, and 1 gallon is equal to 3.785 liters. Most of the time these are given to you. On homework problems, for example, you would have to simply look them up. On exams, they will be given to you because you're not going to be able to look them up on a test. So let's look at the first one. Let's convert the first step to convert minutes to hours. 250 minutes times 1 hour for every 60 minutes. Once again, that hour has got a canceled sign through it. It shouldn't. 4.17 hours. That's 3 significant figures. Second thing, determine the miles driven. 4.17 hours times 68 miles for every 1 hour. Remember, we're going at 68 miles per hour. That's 284 miles, 3 significant figures. You're only allowed 2 significant figures. Keep that in mind for the next steps of the problem. Once again, remember miles haven't been canceled, neither have hours. Step number 3, that's on the next slide, slide number 18. 284 miles times 5,280 feet for every 1 mile. That's 12 inches for every 1 foot. Times 2.54 centimeters for every 1 inch, times 1 meter for every 100 centimeters, times 1 kilometer for every 1,000 meters, is equal to 457 kilometers, which in two significant figures is 406 kilometers. Notice in this time, the only units left over are kilometers, as they should be. Determine the money spent. 284 miles times 1 gallon for every 32 miles times 3.785 liters for every 1 gallon times $0.82 for 1 liter is equal to $27.62, which in 2 significant figure land is $28. So you can see that a multi-step problem can be done very easy if you simply keep track of your units. So let's look at a summary here. Errors occur. One of the summaries, and this, once again, this is for both this discussion and the previous one, which had to do with significant figures. If you haven't listened to the significant figures one, you should. One of the things we said there was that errors occur during scientific measurements, regardless of how careful one is. To be able to convey accuracy to somebody, we have to use significant figures that allow us to convey the precision of our measurements to our audience. The units are as important as numerical values. Without the units, we have no idea what we're talking about. In conversion factors, we use equivalence ratios, and they allow us to relate a value in one unit to another unit, or to in one unit set to another. So, for example, to be able to convert between English and metrics, from inches to meters, from liters to gallons. And dimensional analysis is a way of using one or more equivalence ratios to solve the problems, and that's what we've shown in this discussion. If you're listening to this and you're part of a Chem 4 class, the very first experiment you do, which is a dry lab experiment, is nothing but a large number of significant figures, significant figure terminations, mathematical calculations, and then a bunch of dimensional analysis to get you in the habit of doing it. Finally, I'd like to say that if you have any questions or any comments, you can contact Dr. Hader at chemcook@gmail.com. If you are on campus, you can also get me at chager@ucsd.edu. The presentation has been brought to you with the generous support of the University of California, San Diego's Instructional Improvement Program. If you have any questions, comments, or wish to use the presentations in your university's courses, please feel free to send an email to Dr. Carl Hager at, once again, chemcook@gmail.com. This episode is Dimensional Analysis. If you have specific comments or questions regarding this episode, please note this in your email. I will try to respond to all emails I get. And I do welcome your comments and your criticisms, as well as whether you like it or not. Certain things that are in this will have to be fixed at some later date, but for the most part, I've pointed out those errors. Thank you for taking the time listening to this, and have a good day. Carpe diem, and I'll be seeing you in the classroom.